Today, we're diving into one of the most fundamental rules of the entire cosmos. Seriously, it's a rule that shapes everything from how your phone's GPS works to our basic understanding of reality itself. We're talking about the universe's ultimate speed limit. So let's start with a wild question. What if the universe had a speed limit? And I don't mean like a suggestion. I mean an absolute, unbreakable law that's just woven into the fabric of space and time. It sounds like something out of science fiction, right? But this law is the bedrock of our reality.
To really get why this speed limit exists, we have to go back in time. Back to the late 19th century, when physics was staring down a total crisis. The two great pillars of science were on a collision course, telling two completely different stories about how the universe should work. Okay, so on one side, you had Isaac Newton. His rules were elegant, they made sense, and for 200 years, they just worked. If you're on a train and throw a ball, you just add the speeds together. Easy. But then on the other side, you had James Clerk Maxwell's incredible equations for electricity and magnetism. And buried deep inside them was this bizarre prediction that the speed of light, what they called c, should always be the same. For everyone, no matter how fast they're moving. See the problem? These two ideas just couldn't both be right. Something had to give.
So, to settle it once and for all, an experiment was needed. Two physicists, Michelson and Morley, built this really clever device to measure the speed of light. See, the Earth is whipping through space, right? So according to Newton, they should have measured light moving faster in the direction the Earth was going and slower across. And the result? It was a total shock. They found nothing. No change. At all. The speed of light was just stubbornly, impossibly the same in every direction. It was like the light just didn't care that the Earth was moving. This result made absolutely no sense. And it meant one thing: the old rules were wrong. Physics had hit a brick wall. And this is where a young, unknown patent clerk named Albert Einstein walks onto the scene. Instead of trying to fix the old, broken system, he did something way more radical. He decided to just tear it all down and build a completely new foundation for reality based on two brilliantly simple rules. First, he said the laws of physics themselves have to be the same for everybody as long as you're not accelerating. There's no special correct point of view in the universe. And second, and this was the huge leap, he took that weird result from the Michelson-Morley experiment and just made it a law of nature. The speed of light in a vacuum is constant, for everyone, always. He basically decided to trust the experiment over centuries of what felt like common sense.
Now, if you accept those two rules as true, you're forced into a really strange conclusion. If the speed of light is absolute and never changes, then something else has to be flexible. And Einstein realized that something else was our everyday ideas of space and time.
You see, Einstein's big idea was that space and time aren't separate things. They're actually woven together into a single, four-dimensional fabric he called space-time. Think about it. Any event in the universe doesn't just happen at a place, it happens at a time. It's all part of one unified coordinate system for reality itself.
And we can actually draw this. A space-time diagram plots time on one axis and space on the other. So any single point on this graph, that's an event. It's a specific location in both space and time. And this leads to this amazing visual idea called the light cone. Since nothing can go faster than light, this cone basically shows you your entire possible universe. Anything that could have possibly affected you is in your past light cone, and anywhere you can possibly go is in your future light cone. Everything outside that cone, it's simply off limits. It's the ultimate cosmic boundary.
But this whole space-time idea isn't just some neat mathematical trick. It leads to some genuinely weird, mind-bending consequences for how we experience reality. And the craziest part, we've proven they're true over and over again.
Let's start with a thought experiment. Okay, picture this. You're standing still, and you see two lightning bolts strike at the exact same instant, one on your left and one on your right. To you, they happened at the same time. They were simultaneous. But were they really for everyone?
Now, let's imagine your friend flies by in a super-fast rocket, right between the two strikes. From their perspective, they're moving towards one of the lightning bolts and away from the other. And remember, the speed of light is always the same, so the light from the strike they're heading towards is going to reach them first, right? For them, the two events absolutely did not happen at the same time.
So what does this mean? It means there is no universal now. Whether two things happen at the same time completely depends on how you're moving. Your present moment is, well, It's personal. And that is a truly wild thought.
Okay, let's take it even further with another famous thought experiment, the light clock. It's super simple. It's just a pulse of light bouncing between two mirrors. Every time the light hits a mirror, the clock goes tick. Easy enough, right? But now, let's set that clock in motion. From our point of view, standing still, we see that light pulse now has to travel a longer diagonal path to get from one mirror to the next. But, and this is the crucial part, the speed of light has to stay the same for us too.
And this leads to an amazing conclusion. If the light has to travel a longer distance, but its speed can't change, then it simply must take more time to make the trip. The moving clock literally ticks slower than our stationary one. And this isn't some mechanical illusion. Time itself is slowing down for that moving clock. It's a real phenomenon called time dilation.
This brings us to the famous twin paradox. So you've got two twins, let's call them Alice and Bob. Alice hops in a rocket and takes a trip at nearly the speed of light, while Bob stays on Earth. In the language of space-time, they're taking two very different paths, or world lines, through the four dimensions of reality.
It's kind of like taking a shortcut on a map. It turns out that Alice's high-speed path through space-time is actually shorter than Bob's long, meandering path just staying on Earth. And because her path through space-time is shorter, she literally experiences less time. When she gets back home, she will be physically and biologically younger than the twin she left behind. It's not a paradox at all, it's just the weird, warped geometry of space-time.
Now, I know what you're thinking. This all sounds incredibly abstract. You know, light clocks, twins, and rockets. What does any of this have to do with you? Well, it turns out you use these exact principles pretty much every single day. Think about the GPS on your phone. It works by talking to a whole network of satellites orbiting the Earth. Those satellites are moving incredibly fast, about 14,000 kilometers an hour. Because of that speed, their super precise atomic clocks are actually ticking just the tiny bit slower than our clocks down here on the ground. It's a minuscule difference, but if the engineers didn't account for it, your GPS would be off by about 10 kilometers every single day. It would be totally useless.
So yeah, this isn't just theory. The strange and beautiful logic of special relativity is literally built into the technology that you hold in your hand. Every time you open up Google Maps, you are proving Einstein right.
And that really brings us to the big takeaway here. The speed of light isn't just a cosmic speed limit. It's the one constant thing that forces everything else, space, time, even the concept of now, to be flexible and relative. And it really makes you wonder, doesn't it? If time itself is an absolute, what other fundamental parts of our reality are just waiting for us to look at them from a new perspective?